Okay, let's see. We're not doing hashing anymore, we're doing B trees. Okay, so that's wrong. I must admit that I was writing these notes while I was giving out candy for Halloween, so anyway, there could be other issues. Let's see, what else is here? Oh yeah, the programming assignment is due tonight. Midterm 2 is next week, Thursday. And homework 3 is due a week after that. Yeah.
The electric off for the...
I think it's tomorrow. No, Monday. Tomorrow is Saturday. Yeah. And so B trees will be fair game for the midterm. And we might even get to start on heaps. We'll see. Okay, so as a warm-up though for B trees, let's look at the following tree, which is an M-ary search tree. At least I claim it's an M-ary search tree. Is this an M-ary search tree? Maybe you can't see this. Is that an M-ary search tree? Remember, M-ary search trees are just like binary search trees. It's just that they have the possibility of having more than 2 children if n is large. What is m in this particular case? 5. So we have m equals 5. Every node can have at most 5 children, which means there are 4 splitter keys in each node. So the keys that tell you which children to go to, there are 4 of those. And it looks good to me. I mean, we've got one subtree that's all smaller than 17, another one that's all bigger than 17, and we could check the other ones as well, but I think we're okay. Is it okay? So this is an M-ary search tree. But it's a kind of a special M-ary search tree. What's special about it? Besides the fact that m equals 5. I mean, what do you notice about it that's kind of special? Yeah. Oh, good point. So all the empty children are on the right. This is a consequence of my implementation brain. So in my implementation brain, I think of this as being a vector of key values that you would check when you're looking for which subtree to go to. There would be a vector of key values. It would be of length at most m minus 1. And then there would be a vector of pointers, which would be the pointers that you would follow if you found that your key value that you were looking for was between 2 of the splitter key values. So I think there's an array here. And I want the array to be sort of moved to the left so that I can step through the array. So yeah, it's true. This is a special, you could imagine sprinkling them around all over the place, but essentially it would be the same picture. It's just that I would draw it a little bit differently. But anyway, you're right. That's my implementation brain. Anything else that's, yeah?
I'll just recall what the M represents in this case. Again, I remember from the previous class, you said that the number of split points is at most n minus 1.
Right, because the number of children is at most m. It's like a binary tree. So wherever you see M-ary trees and you get confused, don't be confused. Just remember binary trees. Binary trees are trees that have at most 2 children. They could have one, there could be 1 child, there could be 0 children, but at most 2. So binary and M-ary, so a 2-ary tree is a binary tree. Yeah?
It doesn't matter where like the pointers point to, because I see like they always put in the middle.
No. That's only a figment of this representation. Is that a figment? Oh, anyway, it's just the way I chose to draw them. What it means is that the pointer is a pointer to the structure that contains that array. And in fact, that structure contains more than just that array. It will contain an array of pointers as well. So there's lots of stuff, and this is just a picture for it. Okay. Anything interesting? Yeah.
Is it because it's like perfectly balanced, like everything on the same level? All the children are on the same level?
All the leaves are on the same level. Yeah. All the leaves are at the same depth. That's an interesting thing. All leaves are at the same depth. That's not normal. I mean, if it was like a binary search tree, you could have these binary search trees that sort of go off to the left all the way down. They'd be like long chains. This doesn't show a long chain. It's an interesting M-ary search tree. Certainly M-ary search trees could be unbalanced because M-ary search trees are just like binary search trees. They could all have all of their children be left children. I mean, well, leftmost children, and then they would be just a long chain. But this particular M-ary search tree is nice. It's kind of every leaf is on the same level. Not only that, there's something else that's nice about this tree. To make it sort of fat and shallow, wide and shallow. What else is there in here? I'll give you a hint. There are no nodes of degree 1. There are no nodes that have just one child. That's interesting. And in fact, most of the internal nodes have lots of children. Well, lots for this is 3. So that's another good thing, is that only the root is different. Everything else, every other node has at least half of the children that it could possibly have. Every internal node. Do you know what an internal node is? Did I tell you what an internal node is? No? Guess. What is an internal node? Is this an internal node? No. Is this an internal node? Yes, it is. Sorry. And so are all these. So everything that's not a leaf is an internal node. Every internal node, i.e. a non-leaf. We went through so much terminology, and I forgot that one. Okay, anyway. Every internal node, non-leaf, has greater than or equal to half of the maximum number of children, except for the root. That's another interesting property of this tree. Why are those good properties for a search tree, an M-ary search tree? I claim they're good. In what way are they good? Could we have an M-ary search tree that looks like this? Is that a possible M-ary search tree that satisfies these properties? All the leaves are at the same depth, that's for sure. But is it true that every internal node has half the maximum number of children? This is for m, again, equal to 5. No. These internal nodes, this is an internal node, it's not a leaf. It doesn't have at least half children. It has only one child. It doesn't have like 3. So these two properties that we observe in this particular tree, that all the leaves are on the same, all the leaves are on the same depth, and every internal node has greater than half the max of the children, this is another balance criteria. So trees with this property have log base m of n depth. And trees with these properties, these are B trees. So now you know what a B tree is. B tree is just a specialized M-ary search tree. All the leaves are at the same depth. And internal nodes have between m over 2 and m children, except for the root. The root is special. It has between 2 and m children. And then the leaves hold between m over 2 and m keys in them. This is an additional property of B trees. Everything's pretty much half full or more in a B tree. There aren't any things that are like, one key is sitting around in an array of size 17. That never happens in a B tree unless it's the root. All the nodes are more than half full. And these two properties, are enough to guarantee tree is shallow. Just like we had, AVL trees had a height condition on their siblings. The height had to be within one of each other. And that was enough to guarantee that there was balance. Here, these two properties guarantee that the tree is balanced. It's a different property. It's actually interesting. And it's the basis for B trees. And what's sort of interesting is that with just those two properties, you can show that the height is something like log base m of n, where m is the out degree of the nodes, the number of children, the maximum number of children. Right? Because every node in the tree has more than m over 2 children. And if you remember how we think about this, remember when we were trying to show the height of an AVL tree, that the height was short? What we did was say, we took and said, what's the fewest number of nodes that we could use to make an AVL tree of height h? Remember that? I said, what is the fewest number of nodes? You can do exactly the same thing here, and rather than using log base 2, you use log base m, because the branching factor, the number of children for each node, is at least m over 2. So you would get something like log base m over 2 of n, which is, I'm calling that theta of log m, log base m of n. You can do the same argument. Okay, that means if the height is if it's short, if the tree is only log base m of n high, then all of the operations that we would like to perform on it, we're going to show are going to be able to be done in log base m of n time. Just like in an AVL tree, except now we've got this parameter m, which we can make big. Do you remember why we want to make m big? Remember, m is the number of children of a node, maximum number of children of a node. Why do we want to make m big? Yeah?
So runtime is faster since at each node there's more choices to jump through, which decreases the number of possibilities every time you jump.
Yeah, that's exactly right. Every time you pick up a node, you're getting m or m minus 1 or, well, m over 2 keys to compare against. And that's allowing your search to differentiate between many different branches, which means that you don't have to go out to disk to bring in the next node, except after you've determined that it's within a small range of possibilities, and then that hopefully, and as we see it actually does, will decrease the number of nodes that you have to bring in from disk over a binary tree. Like this is only bringing in log base m of n nodes, whereas a binary tree you would be looking at log base 2 of n nodes. So increasing the m decreases the number of disk accesses. So for big M, we decrease disk accesses over just regular old binary trees. There, of course, is a limit here. We can't just choose M to be a bazillion, gazillion, trillion, because the size of a block of memory that's on the disk, the amount of information that we pull from a disk, is limited. And then we tailor M so that the information that we need in order to represent a node in this tree, in this M-ary tree, fits on a disk block. So that when we go out to disk, we page in an entire node. But that for, these nodes are big. They're like, the disk blocks are big. They're like, thousands of bytes. So you can put hundreds of keys on a node. And so M is now not just some dinky little constant. It's like 100 or 20 or 400. It's big. Yeah.
So, what is that third requirement for these trees?
The leaves?
Is that just so you bring in a lot of information?
You mean for the leaves, right?
Yeah.
Well, it doesn't really matter that much because leaves don't have any children. But in bee trees, you typically will see half full leaves. That reduces the number of leaves that you have by some amount. Like you could imagine having a node that's full of like 100 different, internal node with 100 different children. And each child is space for 100 different keys in it. It's a leaf with 100 different spots in it for data, and only one spot is occupied by data.
So that's not a bee tree.
That's not a bee tree. It's not full enough, yeah. Every node in the bee tree has to be at least half full, except the root occasionally. The root can be not full. You might ask, why can the root be not so full? What's so special about the root? Well, imagine trying to store very few items in a bee tree. Like you have a bee tree that has nodes which have 100 children, but you're only going to store 3 items in it. Well, you have to do it some way. And the way you do it is by making a root as a leaf that just holds 3 items. Or anyway, we'll see under insert what happens with roots as well. So the number of children that a root has can be anywhere from 2 to m. And the number of keys that it can hold if it's a leaf can be anywhere from 0 to whatever m minus 1 is. Okay, nobody asked me the following question, so I'll ask it. Why did I write order log base m of n? Why did I not write, like I normally do, theta of log n?
Highlight how it changes and increases.
That's exactly why I did it. All we're talking about now really are constant factors. I'm a theoretician. You're in a course being taught by a theoretician, which means you don't care about constant factors, except that sometimes you do. And for disk access, we do, because the whole problem with disk access is not an asymptotic problem, it's a constant problem. There's a constant amount of time that we waste, something like, 10 million instructions worth of time, paging in memory from disk. That's a constant. So if you can live with a constant of 10 million, you don't have to do anything like this. But 10 million is so big that we have to pay attention to it. And so that's the constant we're trying to beat by having m be a large enough constant here to make our height of the tree that we produce small. So in fact, B trees pretty much, you can pretty much store all the particles in the universe on a reasonably sized B tree, meaning the nodes are about size 100 to 200 or something like that. You could store all the particles in the universe in such a thing, which was probably of height something like 9. So 9. That's about the biggest B tree you're going to get. 9 disk accesses. Nothing. Unless you want to catalog more than the number of particles in the universe. You have to go to a different universe. So that's the definition. Does anybody have any questions about the definition? The really important parts are that the nodes contain at least half of their capacity, maybe more. And the second thing, all the leaves are at the same level. Yeah? Okay, what I'm hoping that you're thinking right now is not, like, I don't know why. Like, I wonder if it's sunny outside. Or, why is he still talking? I hope what you're thinking about is, how are we going to perform insert? How are we going to perform delete? All the leaves are at the same level. How do you insert into a binary search tree? You go down to the leaf, and you stick another leaf down. I mean, we don't do that anymore. We can't. That would violate all the leaves being at the same level, right? In this tree, if I inserted something and created a new leaf, then, sorry, that's not a B tree. So anyway, that's what you should be, at least that's what I'm thinking about. It'll be fun to find out. Oh, before we find out, I have to show you this picture, which is an expanded view of the node that's an internal node in the B tree. And it contains, this picture is not even very accurate, really. Not only does it contain keys, and not only does it contain pointers to the children, and not only does it contain left sibling pointers and right sibling pointers, and not only does it contain a pointer to its parent, this is all to make the operations that we'll talk about, insert and remove, more efficient. Not only does it do that, but there's data associated with the keys. So really, I should put down here, not only is there a key in here, there's data 1, data 2, data I. These are the data values that are associated with those keys. So now it's a little bit more accurate. I guess the reason that I put this picture here is exactly to address the issue that you raised by your first question, which is, why are some things empty? And the point is that not all nodes in a B tree have to have the same number of children. Some of them have, well, like we saw here maybe. Oh, no, we didn't. Maybe that's the reason. Well, the root here has 2 children. And each of these 2 internal nodes, the other 2 internal nodes, they have 3 children. But it could be that, one of them had 4 children and the other one had 3 children. Or even one of them had 5 children and the other one had 3 children. There's no, it's not the same number for each of the nodes. It's just some amount of them, at least half, are going to be occupied by keys. That's why I wrote this in red. Each node may hold a different number of items. Okay, now let's get on to, so here's, wait. Now let's do this. Okay, making a B tree. So this is a B tree on the left in the box. It's the empty B tree. It's the empty B tree for m equals 3. Now I know m equals 3 is not very exciting. Like, why aren't we doing m equals 100? Because we don't have enough time for me to illustrate enough insertions into a B tree of m equals 100 until we get to the point where something interesting happens. So we're using m equals 3. Okay, so let's insert the thing. So let's insert 3. What happens on an insert is that if there's room in the leaf, it gets put in the leaf. The root, in this case, is a leaf. there's room in the leaf, we put it in the leaf. And we insert 14. The same thing is true. There's room in the leaf. We haven't exceeded the capacity. In a B tree of m equals 3, that means m possible children, every node can hold 2 keys, or 2 key value pairs. So we still have room, so we can stuff 14 in there. Okay, great. Now what do we do when we insert 1? Care to make a guess before we turn to the next page? What happens when we insert 1? Yeah.
Just make the root, bring the root.
Whoa, sorry. So the idea is make 3. 3 becomes the root, and then 1, 14. Yes. Great suggestion. What happens when you insert into a node that's full, so you go down until you go to a leaf, you try to insert the item into the leaf. If the leaf is full, you split the leaf. You break it into 2. So that's what happened here. We broke the leaf that was 314. We broke it into 2, and then we moved the middle item of the resulting set of items, which is 3 in this case. We move the middle item up to the parent. And we say, hey parent, there's now 2 leaves here instead of just 1. You probably should know about that because you need to create another pointer so that you can point to your new child. So in this case, we create a new root, and it has to point to 2 new children. The original node, maybe that had, we kept it around. The new root points to that, and it also points to the new split child, the new one that just split off. Okay, so the parent gets a new child. Everybody good? Easy peasy, you say. No problems. Really? Yeah.
Could we have brought 14 up instead?
Where would you put 3?
Also, 3 would go with 1.
Oh,
So just have 1 children.
would you want to do that?
Not sure.
So the suggestion was, why don't we, instead of creating this tree, why don't we create this tree? 14, 1, 3, empty. You're cheating. That's not really an allowed leaf. It's not a bee tree because it doesn't have enough things in it.
When you think about at least half the number, half the capacity.
Always has to be at least m over 2. So in this case, it's the number of keys inside has to be at least m over 2 minus 1. Because the number of children has to be at least the ceiling of m over 2. So when we're looking at a leaf, we can look at the requirements. Whoops, there's the requirements. We have to have at least the ceiling of m over 2 minus 1 keys in a leaf. Yeah. If this happens again, yes. So there's more complications. It's going to be great. But the real, I want you to understand that the whole process here is a process of splits that actually will propagate up the tree. So let's see what happens. So in this particular case, if I insert a new item, it doesn't matter which leaf it goes into, there's room for it. So there won't be an immediate split. All right, like if I insert 59, there's no problem. But if I again insert 26, then there's a problem. All right, because now inserting 26 wants to go in the leaf that already has 14 and 59 in it. And so what does it do? It says, okay, I've got to split. So I split the leaf, and in this case the middle key is 26. The 26 gets moved up, and the new child is now the third child of the root. Because remember, we're in a m equals 3 B tree. So that we have 3 children, that's perfectly fine. Did this answer your question? Somewhat? But keep going. You probably have another question in your head, which is like, well, then what happens? Like, now what happens if we get more full things? Or maybe you don't have that question. This is kind of mad. Does anybody have any question about this? Yeah? How about if I put in 5 and 16?
Well, that would go to the same. Once both of those on the middle,
Oh, you want to put one into the leaf that has 1 already?
Yeah.
And then put.
Beside it, and then like 14.
Yeah.
And then you want to add numbers that will affect both of them.
Oh, no. So the trick again is it's sort of like an insert into a regular BST in that you always go down to the leaf where the new key should live. You always go down to the bottom to the leaf. And then you say, I need to be in this node. And the node says, I'm full, go away. And you say, no, split. And so the node splits into 2. It shares the contents between the 2 things that it created. So now they are no longer full, right? They are half full, which is good because you want all the nodes to be half full. So they're now half full. And you also have to do this sort of like tell the parent that there's a new child and give the parent the appropriate key to do the split, right? So go down to the leaf, try to jam yourself into the leaf. If you don't fit, split into 2, tell the parent, hey, here's the new splitter key. So you move the key up, and it tells the parent that there's a new. So this is the whole deal. It's just that the interesting thing is when it happens twice. That's what this shows. So here's a situation where we cram 5 in, and that's fine. 5 goes perfectly fine into the 514 node. And then we try to insert 16. 16 comes down, it says, I belong in the 514 node as well. I'm between 3 and 26. Well, let me cram in there as well. And the thing goes, no, I don't have space for you. So it splits. And it says, the middle key is 14. That's the thing that I've got to tell my parent is the new splitter key for these 2 new children, 5 and 16. And it says, hey, parent, here's the new splitter key. The parent is full. So what does the parent do? Most parents just complains. No, I'm not splitting. No, it splits. It splits into 2, just like a leaf. So just like a leaf, it takes in these in this case 3 elements. It passes the middle one up to the parent, which doesn't exist in this case, so we create a new root. And it keeps only half of the elements, -1, of what it had. So it's now no longer, because you've created a new node at that level, it's no longer overcapacity. It fits. Yep.
Well, how did you determine that we should
14 is the middle key. If you look, this is a really, I have to apologize again. This is a very simple example. And there's only sort of 3 things that are in contention every time. But you should think when you're looking at this example how it would generalize to the situation where n is 100. In that case, you are only going to be full when there's 101 things that go into a node. When you split it, there are going to be 50 in one node, 50 in the other one, and there's going to be one other guy which is going to be the splitter key. 1 plus 50 plus 50 is 101. That's all the people that were in that node. And that splitter key has to be the middle one. It has to be the one that's in between 50 and 50. So it's exactly the middle one.
Also, when we take into account the element that we're inserting, we'll just take a look at all the values in the node that we want to split, and we pick the middle value to bring up.
Correct. Because you're going to be doing the split anyway. You have to take the full node, and you have to copy half of its contents into a new node. And you want to copy those half, like the big half, and copy that into the other node. And once you've copied the big half into the other node, then you know what the middle is. Yeah. Yeah. What if it's odd? Break your ties. I'll show you exactly how to break the ties. Because I'm going to give you I'm going to give you some code. So this is how a B tree grows. It grows in height by the root splitting and a new root being created. Isn't that weird? Like it doesn't grow height by having a new leaf added. That's not what happens. It grows in height by having the entire tree kind of crack open all the way to the top, and there's now a new root. That's when it grows. So whenever it grows in height, what are the number of children of the root? Whenever it just grew in height, how many children does the root have? 2. Because the original root had, it was full. It had like m-1 keys in it, and then somebody tried to jam some child tried to jam another key into that node. So now there are m. It shares them between 2, so each of them have m over 2, m over 2, and then it creates a new root that points at those 2. So now that's sort of the mystery revealed as to why, well, that's part of the reason why roots have to be different. They have to be able to accommodate few children. Yep.
And so when we move the split point up to the parent node, so if the parent node has spot, we just automatically put it in there.
That's right. If it was the case that there was room for the new splitter, which is what it was the case of here, when I inserted 26, then I caused 1459 to split, and the new splitter value, 26, that was propagated up to the parent, it just went into the node, and it stopped. It did not increase the height of the tree. Yep.
So, I was wondering about the definition of B tree.
Yeah?
Because so if n is like 4, right? Then the nodes don't have to be half full, right?
Yeah, they do.
Well, if n is 4, then like it leaves only needs one of these spots, right?
Right.
So it's like, yeah, 3 spots, right?
Yeah. If I have 1 key, how many children do I have? 2. How many children can I possibly have?
4. Well, so you care about the number of children, not the number of keys.
I only am talking about number of keys. I mean, I'll talk about number of keys as well, but you have to understand that the number of keys is always 1 less than the number of children. Yeah, it's a good question. Okay, isn't that cool? It's totally cool. I mean, if you don't think that's cool, then I don't know what. Anyway, if you did find that slightly cool, you should go to this web page. Don't worry, it's in the notes, so you don't have to write it down. And you can click on it, and you will see this amazing animation which I'm not going to show you because, okay, I really don't want to show you because it takes too much time. Should I show you? You won't look at it unless I show you. Okay, I'll show you. Hold on. Wait, push. I have the thing. So it runs a JavaScript thing, or it runs Java. Here's an example of a randomly generated B tree, and let's insert something into it and watch how it works. This is a B tree of order 5. So let's see, what would be interesting to insert here? Well, let's try inserting something big like 1,000. There's 1,000. Well, actually it's 999 for some strange reason. Maybe 1,000 is too big. And now it's telling you it's comparing there, and it's going down there, of course. And then it's going down there, of course. And then it goes in there, and it fits. But now, let's put in something else. How about 940? There's 940. It goes down there, of course. Down there, of course. And then it tries to go in there. Oops, now it's too full. So what do you think it does? We know what it does because I just told you. You split the leaf into 2, and you propagate up the middle guy. Now the middle guy goes up and tries to go into this node. Fortunately, there's room for that in that guy. So now how many more values will I have to insert into this? Well, let's ask 2 questions. How many more until my patience wears thin? And how many more until this node will cause the parent to split? The insertion will cause a parent to split, an internal node. How many more do I insert? 3. 2 will fit, but the third one will cause a problem. Okay? Let me just point out a feature of this thing, which is if you go up into the corner and you click on data structures, and you have a microscope, well, let me just tell you. In here it says dictionaries, binary search tree, rotations, AVL tree, 2-3 tree, 2-3-4 tree, B tree, red block tree, AA tree, skip list, scapegoat tree, splay tree, priority queues, heap, dearray heap, meldable priority queues, leftist heap, skew heap, pairing heap, binomial heap, lazy binomial heap, Fibonacci. This is like a whole data structures class in one application. Cool. And you can run animations on all of them. It's called gnarly trees. Okay. Now let's go back to, my patience has now run thin. So let us go back to what we're doing. Okay, this is the insertion code. And it does basically what we just talked about. Oh, I have a question. I need to ensure that when I perform the split operation, that the resulting 2 nodes that I create are sufficiently full. Could you prove that to me? This is like one of those, this could be a midterm question questions. I tell you, in a B tree, when you split a node because you've inserted too many things into it, into 2 nodes, are you confident that you could prove that each of those 2 nodes still satisfies the capacity requirement, the fact that it has to be at least half full? It's just a question. I don't need you to answer it, but I do want you to think about it. By the way, I haven't written the midterm yet. The remove algorithm is even cooler. So the remove algorithm is essentially the reverse of the insert algorithm. But what it involves is you go find the thing you want to remove, the key that you want to remove. It could be in an internal node. It could be in the middle of the tree. But we know what to do when that happens. We've done it before. We swap the key with its predecessor or its successor so that we know the predecessor or successor of this key is, leaf. We know that. And so we know now when we've done this swap that the structure is correct, except we have to remove the thing we just swapped down to the leaf. So now I've reduced the problem to removing a key, from a leaf. Okay. This is the way it works. To remove something from a leaf, you go down to the leaf and you remove it. And if it works, you're done. But if it doesn't work, which means the number of items that are in the leaf is too few, it's gone below the halfway capacity, the m over 2 thing, m over 2 minus 1, then you're in trouble. So what do? You steal from your siblings. Okay? So there are siblings to your left and right, the ones that are children of the same root, and you, if you can, steal an element from a sibling. This is terrible. This is a horrible thing to do. Why? I mean, not morally speaking, why? Just why is it bad to do in this structure? But why is it bad for me to steal from a sibling in a binary search tree, n-ary binary search tree structure? N-ary search tree structure. Yeah.
Because it can't go up, so you would have to traverse to its closest neighbors, rightmost or leftmost.
Yeah. I should say, if you happen to be the eldest child, the first child of a node, you do not have a left sibling. But you still have a right sibling you can steal from. So it's okay. There's some nodes that don't have as many options, but still I want you to try to steal, or at least that's what I'm suggesting. But I'm also saying there's something you have to be worried about here. If I steal a value from another sibling, what does that do to the parent's keys? Yeah.
It's like
No, go.
for example, right sibling, you're all greater than right?
Yeah.
You steal it from the right.
Yeah, if I'm here I am, I'm this child, and there's another child, and there's a split key 5, and everything over here is, let's see, I'm the younger child, so I'm over here. So I've got, like this one has like a 1 and a 2 and a 3. They got plenty of keys. By plenty of keys, I mean there's enough to steal. Like if I steal one, that child will not be below threshold. But here I am over here, and you're deleting 6 from this node. Then it tries to steal a key from here. Of course, it will steal the largest key because that's the right order to steal in. So it'll steal 3, and it'll bring it over here. But somebody has to tell the root that something's changed. So in fact, what happens is you do steal from your sibling, but you steal that value and you cram it up in the parent. So this becomes 3, 1, 2. That's a 1 and a 2. And then 5 comes down to this child. That's stealing from the sibling. Okay? If stealing from the sibling doesn't work, it means that your sibling is very poor, has no money, has no keys, can't afford to give you one because it would drop below threshold. If you can't do it, what that means is both of you are very, very poor. Both of you have very few keys. What do you think happens? You merge. You conglomerate. You have fewer than m over 2. Your sibling has fewer than m over 2. You put yourselves together, create a new node. That new node has no more than m. And you tell the parent, hey, you don't need to use a splitter anymore because we're now joined at the hip. There's no two siblings. So there's two steps. Try to steal and then merge. Okay? That's what this code says. I hope you have a relaxing weekend.